All right, guys. So here's a couple more examples of the rational zero theorem that we were discussing earlier today. So I kind of want to just go over some more examples so we can kind of see this in motion. So the first thing you want to do is you want to make sure your polynomial is in correct order form. So like when we're looking at this, we want to make sure it's the highest degree is here, and then it goes down in descending order. Sorry. Uh, so looks pretty good to me. So we should be a-okay. So now what we want to do is we want to look at our last digit and our leading coefficient, and this is going to create the ratio of p over q. So this let me use this one. Okay, so this would be our p, and this would be our q. So I'm just going to kind of do it all over here off to the side. So I'm going to have -3 over 1. All right, so this is P over Q. Okay, so what I want to do is I want to make all the possible combinations of -3. So we have -1 times 3, and then 1 times a -3. Those are the only two combinations we have. These two digits and these two digits. So they multiply, they give you -3. And then we kind of want to do the same thing for 1. So it's 1 and 1, and -1 and -1, right? So 1 times 1 gives you 1, -1 times -1 times -1 gives you also 1. Okay. So here we could kind of reduce this, right, to our possible factors. So in this case, we would have -1 over 1, which is just -1, 3 over 1, which is just 3, 1 over 1, which is just 1, and then -3 over 1, which is -3. So this kind of seems kind of common sense, right? But it does make a difference, especially when if our bottom or denominator had been something other than 1, like a 2 or a 4, it would make a difference on that in actuality as far as the negative and positives go. Okay, so now these are our possible factors, right? So these are our possible zeros, right? So these are a list of numbers that we want to test. So what we want to do is we want to take these numbers, these digits, and plug them in to our polynomial. So we kind of want to have this kind of pre-written for us. So I'm just going to kind of rewrite this um, a couple of times, right? You want to test the numbers. And when you test these numbers, you want to make sure your result ends in 0. Okay. The one that ends in 0 is the factor you want to use. So on my first go around, I'm going to try -1. Okay. The second one, I'll try 3. And then 1. And then -3. Okay. Doing this will actually help you kind of understand. Now I know what you guys are thinking. You guys are probably thinking, sir, well, why can't we just plug this into our calculator and into our y equals and just kind of go from there? Well, you actually can do that. And I highly recommend you doing that because that's going to save you time, right? And time is of the essence. So give me a second. Okay, plus x minus 3. So okay, give me a second. So if I plug in -1, right, into all of this, I get a response of -8. Okay, so then this is not a good factor. So we would take out -1. So that -1, we're not going to use it. If I plug in through, well, let's go to 1. If I go to 1, we get -4. So -4 is not 0. So 1 is not a factor. If we go to -3, -3 gives us -60. So -3 is not a factor. And you guys could already know that I skipped number 3 for a reason, because number 3 is actually 0. So this is the factor we're going to use. So now what do? Well, we now know that x is going to equal 3. So we know one factor. So we could convert this into factor form by just kind of switching it. So if it's x equals 3, it becomes x minus 3. So that's one of our factors. Well, we're going to use this number to do some synthetic division. Okay, so our synthetic division, we're going to use this 3, and then we're going to go 1, -3, 1, -3. That's a little odd. Okay, so then this first digit just comes down, and then I multiply. These two digits sum up to 0. 3 times 0 is just 0. This comes down to 1. 3 times 1 is 3. And then we're left with the remainder of 0, which this is perfect, right? So we have a polynomial. So kind of scroll up a little bit. So this would be x squared plus 0x plus 1. Or we could just write it as x squared plus 1. Okay. Now, the neat thing is now this polynomial and this factor is our, this is what we're factoring it out, right? We're breaking it down. So we have one factor, and then we have this one. Well, this one is a special one, right? It's known as a difference of squares, right? So what we ended up happening here is we're going to have a very special, okay, I don't know why this is not deleting, okay. We're going to have a very special case of factors here. So when we break this down, we have something special, right? So usually when you do something like this, or actually I'll come over here to this example, we try to find a list of numbers. Actually, I'm sorry, I said this was a difference of squares. This is not a difference of squares because it's not even a difference. It's got a plus sign. So back of the bus, I correct myself. I don't know why I said that. So right here, usually the little trick is to figure out two numbers that multiply to 1 but add up to 0, right? So we could stay here racking our brain and we'll never find that, right? Because 1 times 1 gives us 1, but when you add 1 plus 1, it gives us 2. It doesn't give us 0. And then we could do the same thing with -1. -1 times -1 would give us +1, but when you add them, it gives you a -2. It doesn't give us a 0. So what do we do in this situation when we have x squared plus 1? Well, we're going to do what we kind of did a while back. I want to say when we did quadratics, we did the square root property. So we set this equal to 0 and solve for x. So we bring the 1 over and get -1. Take the square root. And then so we're going to have plus or minus the square root of -1. Now, square root of -1, we should know that this is just I. So our roots or our factors would be x equals I, x equals -I, and of course, x equals 3, right? So because that was our first one that we came up with. So we could just convert these two factors if you want, would be minus I plus I, and then -3. And this would be our factors, okay? Now, I think on your homework, they're going to ask you for this, the zeros. So you're just kind of solving for the x. So we would have gotten 1 automatically using our P's and Q's ratio, right? We would have gotten one of our answers. And then we use that answer to synthetically divide. And then we break this down using the square root property to find our other two, which is a positive I, negative I. Okay, so we're going to do another problem. Okay, what I'm going to do is I'm going to do number 4 before I do number 3. Okay, and the reason I'm doing number 4 before I do number 3 is because this one is a degree 3, so it's going to go by a little bit faster. Okay, so same thing. I want to get my P's and my Q's, which would be -12 over 1. Okay, so then I want to look for all of my factors of negative 12 and 1, right? So I could go negative 1 and 12, and then 1 and negative 12, 2 and negative 6, negative 2 and 6, 3, negative 3 and 4, and 4 and negative 3. And trust me, it makes a difference. It really does. And then, of course, we have 1, 1, and negative 1, negative 1. So now we have a lot of combinations, right? We have a lot of combinations we could possibly choose. Okay. So the thing is finding the correct combination that's going to work for this, right? So I'm just going to kind of reduce this. So we're going to have negative 1, positive 1. We're going to have 2 and negative 2, negative 3, positive 3, 4, negative 4, 6, positive 6, and then 12, negative 12. So we have so many combinations to choose from. So which ones are we going to plug in to our polynomial such that we're going to get 0, right? So the idea is to get a result of 0. So just like before, we could actually plug this into our calculator, and we could just kind of go down the y equals the table and figure out which one actually works, right? So that's what I'm going to do right now. I'm going to put x to the power of 3 plus 4x squared minus 6x minus 12, right? And I go to I go to table, and I'm just going to check my points. So it's like if I was literally adding negative 1 in here, here, and at negative 1, the answer would be negative 3, right? At 1, if I was to put 1, the answer would be negative 13. So this one doesn't work. This one doesn't work. If I choose 2, lo and behold, 2 actually works. So if I was to plug in 2 here, all the way through, I would get a result of 0. So that means x equals 2. So that is one of my zeros, and that is one of my factors, right? Now I could check the other points. I could check negative 3. I could check negative 6. I could check negative 12. I could check 3. I could check positive 4, positive 3, positive 6, and positive 12. And none of them are going to work except for this 2. So that's perfect. So we only had to check 3 of them before we actually got the factor. So now what do we do? Well, we already got one of our zeros. Now we're going to do our synthetic division. So we take this 2, and we're going to use it to synthetically divide. So we drop down the 1. 2 times 1 is 2. 4 plus 2 is 6. 2 times 6 is 12. Negative 6 plus 12 is 6. 2 times 6 is 12. And we get a remainder 0, which is fantastic. Now we just make this into a polynomial. And now we have x squared plus 6, 6x plus 6. There we go. So now we could do the process all over again, right? We could figure out, we could do this PQ process all over again. So now we know one of them, right? We know that it's x equals 6, and we could do the same process with this one, okay? So usually what we would do here, sorry, let me back up the bus. Usually here we would kind of do this notion, right? What two numbers give us 6 when we multiply them, but when we add them, give us positive 6, right? In this case, I don't think we have a set number, right? We don't have, we have 6 times 1 gives us 6, but when you multiply them, when you add them, that gives us 7, not 6. And then 3 times 2 gives us 6, but when you add them, that gives us 5 and not 6. So that little trick that we use for quadratics doesn't work. So what we're going to do is we're going to use Old Faithful. So let's see if you guys remember what Old Faithful is. It goes like this. and like that, and a little bit like this, and a little bit like that, and a little bit like this, and a little bit like that. So yes, our old faithful quadratic formula, right? So we have a quadratic here, so why not use it? All we have to do is label our A, our B, and our C. So that means we're going to have -6 plus or minus 6 squared is just 36 minus 4 times 1 times 6, which is 24, over 2 times 1, which is just 2. So this becomes -6 plus or minus the square root of 12 over 2, which I could take out a term here, right? Square root of 12. It's 4, 3, so I could break down 4 by 2, 2. So this is actually -6 plus 2 square root of 3 over 2, and -6 minus 2 square root of 3 over 2, which means our answers would be -6 plus the square root of 3, and then -3 minus the square root of 3. So actually, let me write it like this. I'm going to write x equals -3 plus the square root of 3. X would be -3 minus the square root of 3. And then, of course, our original one that we used was x equals 2. So here are our zeros. Now I'm going to do number 3. So I wanted to do number 4 because it was a degree 3, so it's a little shorter. Whenever you have a degree 4, you might have to do the PQ ratio a couple of times before you can actually use either the quadratic formula or the factoring method of that times little times and plus trick that we use for quadratics. So in something of degree 4, you might have to do the PQ a couple of times. So here, the nice thing about this one is our coefficient is still 1 here. So we have 4 over 1. So we're not going to have too many factors. We're going to have 1 plus and minus 1 plus and minus 2 and plus and minus 4. So we only have 6 possible numbers we're testing, as opposed to like 12 over here where we had, I don't know how many numbers did we test with 2, 4, 6, 8, 10, 12 numbers, right? Here we only have 6 that we test. And luckily for us, we still have our handy dandy calculator that we could just plug in and we could just check for the results, right? Because we're plugging them in as X. We're not plugging them in as anything else. So yeah, so I'm doing that right now, and I'm just gonna test each one of these. So when I test 1, I get a result of, well, I get a result of 1. I mean, sorry, as a result of 2, 0. -1 would be 60. 2 would, I don't know why I'm putting commas. 2 would result in 6. -2 would result in 234. 6 would result in, well, -6 would result in 427. 0. And then +6 would result in 130. So had I put each one of these numbers in for each of these x, -6 wouldn't have worked, +6 wouldn't have worked, -2 wouldn't have worked, 2 wouldn't have worked, -1 wouldn't have worked. The one that would have worked would have been 1. So lo and behold, our very first one that we chose would have worked. Okay, so that means we have one of our answers. One of our answers is x equals 1. But this degree 4 tells us that we should have 4 of them. We should have 4 of these x's, right? So like over here on number 4, we had a degree 3. So we ended up with 3 x's, right? So here we have a degree 4. So we should end up with 4 x's. So we got 1 out of the 4. So that's good. That's something, right? So now what we're going to do is we're going to use this to synthetically divide. So we got 1, -9, 25, 21, and 4. Okay, I bring down the 1. This becomes 1. This becomes an 8. This becomes a -8. This reduces to 17. And then that would be 17, which would be -4. And that is perfect because now we get a 0 remainder. Okay, so now using synthetic division, I have to convert this to a new polynomial. Oops, there's the x. So now we're stuck, right? What do we do here? Well, we're going to have to do the same scenario, right? So we're going to do another PQ setup, but now we're doing it to this polynomial. So we already got one factor, which is great. I'll highlight it. But now we have to do this PQ now in terms of this polynomial. So it's like a whole new problem, right? So we're just kind of breaking it down. So again, we're going to have plus and minus 1, plus and minus 2, and plus and minus 4. Right? So these are the factors of -4, right? So now all we have to do is go back to our calculator, type this in, and see which ones work. X squared plus 17x minus 4. Okay. So -4 would be -264. -2 would be -78. -1 would be -30. +1 would be 6. +2 would be 6. And lo and behold, 4 would be 0. So notice these wouldn't work. These do not give us a result of 0. So if I had plugged in 4 for x here, my result would have been 0, and that's what I want. So I just found another factor, x equals 4. Okay, just found another factor. So not only do we have x equals 1, we also now have x equals 4. So we have 2 out of the 4. So what do we do with this? Well, we use it to synthetically divide once again. So, whoops. Give me a second. So we're going to have 4, and then we're going to use this polynomial. 1, -8, 17, -4. This equals 4. This would be -4. This would be 16, -16. 1, 4, and this is perfect. We get 0. So we should, right? Because that's why we're using these rational zero theorem, factoring theorem, and all these good stuff. So we should be able to get this under control. Okay, so now here's where we usually use that little trick, right? What two numbers multiply to 1 but add up to -4, right? And we're gonna get stuck, right? We're going to get stuck because there is no number that multiplies to 1 but adds up to -4. However, what we can do here is, because this is a quadratic, we could use our old faithful, our quadratic formula, right? Just like in the previous problem. We use this bad boy, right? And this is the king, guys. We want to use them, right? So a negative would give us a +4. -4 squared is 16. -4 times 1 is just -4. -4 times another 1, right? So it's just -4 over 2. So this becomes 12. So we're kind of left with almost a similar answer as before. So we're going to have 4 plus 2 square root of 3 over 2, because the square root of 12 is 2 square root of 3. And then we have 4 minus 2 square root of 3, right? And then we just reduce the 2's and the 4's. and we're going to be left with x equals 2 plus square root of 3. X would be 2 minus square root of 3. And then, of course, our other factors that we found earlier were 4 and 1. Oops, 4 and 1. And lo and behold, we got 4 answers for x. So, and that makes sense because we had a degree 4. So we're using this method, guys, to find how many zeros we have. Now, I know we could possibly um, put this in Desmos, right? And just kind of see where the graph hits the x-axis. And that would be fine when the numbers are nice, like 4 and 1. But when they're not nice, like square roots of 3s, that's kind of hard to pinpoint, right? You're going to have a decimal, right? Or if they were imaginary, like the previous problem that we had, right? If they were imaginary, then they don't actually cross the x-axis, right? So that's why this rational zero theorem is very powerful, because no matter what type of answer they give us, whole numbers, decimals, imaginary numbers, you're going to get the answers. And this is why we study it.